It's my great pleasure to have Professor Joseph Sifakis today at the diiP Distinguished Lecture Series. Joseph is a distinguished researcher. He's the only French winner of the Turing Award, which is the equivalent of the Nobel Prize for computer science. And he received this award for his contribution to the theory and application of model checking. So he has worked a lot on verification techniques. This is what he was doing for a number of years at the Verimag laboratory at the University of Grenoble, which he founded. And he is now doing research on autonomous systems. He's going to talk about this today and the repercussions of machine learning and verification in this context. Joseph, the floor is yours.
Thank you for the introduction. So let me share my screen. Let's see. Can you see my screen?
Yes. Yes.
Yes. Okay. Thank you for the introduction. It's a pleasure to talk about, in fact, testing system intelligence. I'm not an expert in AI. I have a systems engineering background, so I will take this perspective. And in my talk, I have three parts: where we are, so where artificial intelligence is standing today, in my opinion, where we go, and the key topic that is testing system intelligence. To start, I will say that there is a great deal of confusion as to the final objective of AI. Opinions are divided between two different positions. And this reflects, in fact, the lack of agreement on what intelligence is. Some AI research and companies like OpenAI and DeepMind see artificial general intelligence as the ultimate goal. And this vision considers that machine learning is the end of the story, I think. They focus on building super intelligent agents that are capable of analyzing large data sets. Okay, I mean, you know all this. And then there is another position that I adopt to say that the goal of AI is building machines with human-level intelligence. Of course, this requires agreement on what human intelligence is, and this is something I'm going to discuss today. But I think that if you open a dictionary, you will see the definition, a commonly accepted definition of intelligence. It's the ability to learn, understand, and think in a logical way about the world and act purposefully. So machines today can do impressive things, but they cannot surpass humans in situational awareness, adaptation to challenges, and creative thinking. Now, so today I believe we have something that I call weak AI that gives us the elements to build intelligent systems, but we have no principles and techniques to synthesize them. And this AI focuses on intelligent assistants that are conversational systems, in fact. And I believe that for the future the monitors and controllers, and these are very, very important applications. So what does a monitor? A monitor monitors parameters, thousands of parameters of a system, and produces knowledge. And an AI controller is an end-to-end controller that can be used for autonomous, for driving cars, if we are successful in building AI controllers that are trustworthy enough. So for me, what we have today with ChatGPT is not the end of the story. There are a lot of interesting developments in the future. And I would like to talk here about autonomous systems that, in my opinion, are a step toward building systems that exhibit human-level intelligence. And these systems are composed of many agents the agents are pursuing their individual goals, but should collaborate to achieve also global system goals. And the agents should be able to manage dynamically changing sets of possibly conflicting goals, cope with uncertainty of cyber-physical environments, and harmoniously collaborate with human agents. And you understand that autonomous systems support a paradigm of autonomous systems that goes far beyond the machine learning systems. This is something I'm going to explain. And today, the autonomous vision is hampered by the non-explainability of AI systems and also by difficult systems engineering problems that are unrelated to the fact that the agents are intelligent. At present, we have two different technical avenues to build autonomous systems. One is to take the traditional critical systems engineering approach that we applied successfully to aircraft production systems. But this approach is defeated by the complexity and the heterogeneity of autonomous systems. And another approach that is taken by industry is to build end-to-end AI-enabled solutions that fail, however, to provide the required strong trustworthiness guarantees. Now, the question is, I'm going to talk about risk. We know that AI systems are known to be black boxes, and so the issue of risk has been discussed, has been a concern for authorities, for institutions. Recently, we had a summit in London to discuss about safe AI, and also everybody agrees today that we should have some kind of worldwide AI governance, and of course, each one of the key players, the United States, European Union, and China, have their vision about that. I'm not going to give details, but probably you know that this period of the year, we have a lot of discussions in the US. They published the AI executive order. You have many Chinese texts that have been published recently. And in Europe, we have texts that define a rigorous framework for risk management, and in particular, the AI Act is currently discussed in Brussels. Probably you've seen this in the news. And also another European text is the Digital Services Act that regulates platforms, very large platforms, and defines obligations for the key players, the key platforms, to which the platforms must comply by February this year. So Europe is very active in regulation. Now, of course, the question is, when you have regulations, how you check that these regulations are applied. And this is the topic of my talk, how you check that the system is trustworthy, which means for traditional systems that the system is safe and secure. You see here definitions of safety and security. But for AI systems, the discussion goes far beyond this type of properties. Some papers, many papers, consider that AI systems should meet human-centric ethical principles, and I give a list of such principles. I let you read, so you have many papers discussing all this. However, all these works lack foundation because they ignore a very basic epistemic principle. If you claim that the system satisfies a property, this should be substantiated by a rigorous method of validation. So in this talk in particular, we'll discuss this very important issue, whether the properties of AI systems can be guaranteed in the same way as the properties of traditional digital systems, and to what extent, what we can learn from traditional systems engineering, and whether the methods are transposable to AI systems. So now let me talk about testing system intelligence, which means that testing properties of intelligent systems. And by the term intelligent systems denotes any system that exhibits intelligent behavior. And of course, intelligent systems should integrate AI systems. So the idea to compare human and machine behavior goes back to Alan Turing, as you say, who proposed the famous test, where in two different rooms you have a machine A and a human B, and an experimenter C sends written questions and collects the corresponding answers. And Turing said, if C cannot tell which is the computer and which is the person, then A and B are equally equivalent. I mentioned this test because there is still a lot of discussion. Many people claim that the system are intelligent because they passed the Turing test. And I think that the Turing test is not adequate to compare human and machine intelligence for many reasons, because you have a human judgment. So C is a human and the judgment is subjective. Also, you can choose the test cases, but you can introduce bias in the test cases. For instance, if the question is, give me a good approximation of square root 2, the machine will do better than the human. And of course, the test cannot be a question-answer game. It's clear. So in a paper some years ago, we proposed another test we called the replacement test, where we say that an agent that can be a machine or a human is as intelligent as an agent B if the agent B can replace the agent A successfully. Sorry, an agent is as intelligent as B if A can successfully replace B. For instance, I will say that a machine is as intelligent as a human driver if it can successfully replace the driver, or a human is as intelligent as a cleaning robot if the human can replace the robot. And it's clear that the replacement test applies to autonomous systems, while the Turing test is a special case for conversational tasks. Now, deciding this kind of behavioral equivalence relations, either the Turing test or the replacement test, or there are other tests in the literature, boils down to testing that the system of which we know the behavior, say this is a function for X, you get the output Y, satisfies a predicate that is a relationship between input and output. And so for the Turing test, this relation will be satisfied if Y is a correct answer to a question X. And for the replacement test, this relation will be satisfied if Y is a safe trajectory for a driving scenario for a car. So everything boils down to testing, and testing is an essential part of the scientific method that is applied in any scientific discipline to produce empirical knowledge. I would like to emphasize here that it differs from verification, because verification is validation by reasoning on a system model. And because of this difference, we can validate properties that can be observed, only can be captured by this input-output relationship. And so if you apply test methods, you have to apply a large number of tests and to have some method to do that. And also, I would like to say here that testing is a very basic validation technique for traditional systems, and there are theories about how to do that. Now, the important question is to what extent we can apply test methods to intelligent systems. But before I discuss this, I would like to make some clarifications because it's important that we agree on a terminology. First of all, it's clear that we have two different computing paradigms. We have traditional computers that execute algorithms, can be understood and verified, and neural networks that are systems that produce the data-based knowledge, and as I will say, they are not explained now. So neural networks are artifacts. They are not models. There is a lot of confusion because the AI community calls the neural network models. And for me, models are representation of things that we use to explain and understand reality. And these are essential, as I said, for science and engineering. Also, it's clear neural networks do not execute algorithms. We use algorithms to train them. And the best way to understand the difference between neural computing and traditional computing is to think about the difference between System 1 and System 2 of Kahneman's systems. So System 1 is fast thinking, deals with implicit knowledge and is closer to the neural network paradigm, and System 2 is close to the traditional computer paradigm. Now, something else I would like to clarify is that this concept of explainability, because many people talk about AI, they want AI to be explainable for obvious reasons. And what it means that the system is explainable. It means that its behavior can be described by a model, in the sense I have defined a model that can be analyzed by reasoning or can apply analysis techniques. And models are basic, any scientific and technical approach is based on the use of models. Now, for neural networks, what it means that they are explained. It means that because a neural network is a kind of circuit, we have inputs and outputs, and we perfectly know the behavior of a node. So behavior of a node is the weighted sum of inputs where we apply some activation function. So this is perfectly known, and theoretically it's possible to compute a function that relates the input variables to the outputs. Of course, this approach does not scale up from a real neural network, and my conclusion is that neural networks are explainable. However, there are papers that talk about explainability of neural networks. These are weak notions that do not provide a basis for verifying properties. If you have questions, we can discuss this. Now, let me come to the important question, what it means to test a system. As I said, the test is a universal method for producing empirical knowledge. So I have a system with inputs X and output Y, and I want to validate a property that is a relationship between inputs and outputs. And in a test framework, I apply inputs, I observe the corresponding output, and here I have an oracle. This is established terminology to decide whether a property PXY holds. And the oracle so is a person or a system that produces verdicts, pass or fail. So the important question is whether we can develop a test method to decide how to choose the test cases, because of course we can apply randomly inputs, but for systems that have a very, very large number or an infinity of possible input values, it's hopeless. So we need a method. And that's the method. A method says how to choose among the possible test cases and decide whether the process is successful or not. And in any test method, in fact, you need the two functions. Coverage function, and the coverage function gives for a set of test cases the probability that you explore some part of the system, okay, in relation to the property P that you want to validate. And the score function measures for a test set, so for a set of experiments. So X, capital X, is the set of test cases, Y is the corresponding responses, the likelihood that S meets P. So whenever you want to have a test method, you need these two functions. And there is a very strong requirement that relates the two functions. This, what I call, or some people call, the reproducibility requirement. If I have two test sets that have the same coverage. So you see the set of test cases have the same coverage, then the score is more or less the same within some margin that can be estimated by the theory. And this is something, this is a requirement that guarantees the objectivity, in fact, of the results. Now, here I try to show the differences in the applicability of test methods for classical systems or for intelligent systems where we don't have a model that describes the behavior of the system. Now, if you apply test methods in physics or of flight controllers, you have a model of the system, you can reason about that, and you can have some very strong evidence about the satisfaction of the properties validate. And then in medicine, for instance, you can apply statistics-based techniques, for instance, to estimate the efficiency of a vaccine. Applied statistics provide methods to do that. And then here I'm showing three different types of systems. It's clear that for ChatGPT, you cannot apply the scientific method because the Q&A relations are in natural language. You cannot rigorously express this. And of course, a human oracle will apply subjective criteria. However, for other types of systems, you can have some formulation of the property P you want to validate. And what is missing is a test method. And test method will require some model to reason about, and this is missing today. So just to summarize, the application of test methods to intelligent systems is limited to properties of technical terms like safety or security that should be rigorously specified, and this excludes language, natural language transformers, and that can be observed. So in some human-centric properties like intentionality, belief, awareness are not observable. And something else I don't have time to discuss is that this reproducibility requirement is jeopardized by adversarial exams, if you see what I mean, for neural networks. Now, just to give you an illustration of the practical difficulties we have when we are trying to apply test methods to intelligent systems. I work on self-driving cars. Recently, there has been or I don't remember, yes, in 2019, you had Waymo published this information. We've driven 10 billion autonomous miles in simulation, claiming that their system is safe. Of course, this argument is not technically tenable. Why? Because they don't explain how a simulated mile is related to a real mile. And in order to do that, you need some evidence, and you need the coverage criteria that the simulation deals fairly well with the many different situations. And this is missing, in fact, in their report. And so we need the test methods for self-driving cars, but for other kinds of intelligent systems. And I think repeatability will be a very, very challenging issue here. Now, just to show you the technical difficulties we are facing when we try to validate intelligent systems like self-driving cars, you need a very good simulator. And a simulator that is realistically models the behavior of the system. So here I have agents that can be pedestrian or can be vehicles. You need a model of the external world because you need to represent the model world and all the geometry, the geometric characteristic of the external world. And then now to test, to see for programs, testing test cases are simple. These are vectors, input vectors, okay? And here you need to provide scenarios. So scenario is a sequence of steps that each mobile should follow here. And of course, to generate the scenarios, you should the scenario should be context aware. You cannot ask a vehicle to turn left if turn left is not possible. And then, of course, when you apply scenarios, you can observe a system run. So a system run is a sequence of states, the trajectories of the vehicles, and you can, we have theory for that, how to formalize the properties. The properties are safety properties here, avoiding collision, but also respecting traffic rules. And you have to formalize traffic rules. You need a logic for that, and you can have a runtime checker. We have techniques for that. But you see, the problem is how to put all these things together. And there are discussions about standards, how to describe scenarios, how to describe properties. So it's a non-trivial problem, the validation of self-driving cars. And in this slide, I summarize all of the difficulties. You need a coverage criteria or functional criteria, and also verdicts and diagnostics about the relationships between the failures and the various risk factors. And today, most simulators provide just a report saying, I disengaged the autopilot without any further explanation. And currently, I work on this problem, how to develop a test method for autonomous vehicles. And the idea is to apply some compositional techniques. I don't want to give details, but the results we get are very surprising. We apply these results, so the test method, to real systems, and we find a lot of flaws that we would not have found by random testing. So if you have questions, we can discuss this. Now, this is the last part of my talk. I'll talk about the future. What are the important problems, in my opinion? So the first problem is that we should agree on a concept of intelligence. As I said, there is a lot of confusion. People talking about AGI do not provide any clear definition of what they want to do. Okay, my opinion is that there are multiple intelligences, each characterizing the ability to perform tasks in the different contexts, and this is an idea that you can get from autonomous systems. And of course, to say that system S1 is smarter than system S2 is meaningless if you don't specify the tasks they perform and the success criteria. It's clear. Now, if the purpose is that we build systems matching human intelligence, we should also understand that human intelligence is not a general purpose. It's the result of historical evolution in a given physical environment. I think that if humans were living in a different planet, they would have a different kind of intelligence. So if human intelligence is the benchmark and the ambition of AI is to build machines that mimic human intelligence, the challenge is not to build machines that execute one task better than humans, but to be able to imitate, to mimic humans. They should be able to coordinate tasks. And this is what characterizes human intelligence, is the combination of skills. I hope you understand this. Something else I would like to emphasize is that, in fact, there is an interesting complementarity between human intelligence and machine intelligence as it is today. So we have AI systems that outperform humans in learning multidimensional data, and humans are very good in abstraction and the management of symbolic knowledge. But humans, we know this, are limited by cognitive complexity. They cannot deal with relations where you have more than, I don't know, 5 parameters, something like that. So the important question is, of course, one can imagine that here we have an agent that combines human and machine intelligence. And of course, the important question is whether we can bridge the gap between symbolic and concrete knowledge exclusively by using neural networks or by using LLMs. LLM can capture some of the semantics, some abstractions of the language. but the question is how far we can go with LLMs alone. The other important question is that, and this is also something that is discussed in the regulations for limiting AI risks, is how we evaluate the properties, how we validate the properties of AI systems, and what are the relevant properties. So today there is a trend to ignore systems engineering criteria. Okay, so many works talk about ethical AI, and which superficially attributes mental attitudes, as I said, belief, desire, etc. And okay, so I found this interesting sentence in a paper, in a research paper. We cannot show that an agent always does the right thing, but only that its actions are taken for the right reasons. Think about that. Now, I think that also it's not enough to set out ethical principles. So even if you take technical concepts like safety, for instance, which is safety is also an ethical principle. The question is how you implement safety for different types of systems. So I have discussed the validation of safety for autonomous vehicles, and you see the problem is very, very different from validation of safety for ChatGPT. If, for instance, you want to test that ChatGPT will not generate deep fakes, this can be considered a safety problem, but you need a very different approach. The problem is very different. Something else that is important to consider, I think, is that for AI systems where we cannot apply the scientific method, we have to study specific techniques between rigorous validation and qualification tests. So somebody can come and say, can we apply qualification exams to LLMs? Because after all, someday LLMs will be able to pass the final exams in medicine. So why LLMs could not operate as medical doctors, whatever. I think that we should think about that, of course, and I have many arguments against this idea, because there are some fundamental differences between neural networks and humans. Human thinking is robust, whereas neural networks are not. So humans can be consistently wrong or consistently right. I mean, if they are not insane. And the human thinking is based on common sense knowledge, as you know, and humans are better placed to avoid inconsistencies in the answers produced, and we know that LLMs can be obviously inconsistent. And of course, human decision-making also implies responsibility for the consequence of their actions. You will not put an LLM in jail, it's clear. So I think that this debate about human-centric properties of AI systems is very, very important, and we should I'm not against the idea that we attribute to AI systems human-centric properties, but we should be very, very careful about that. First, we should understand how these properties characterize the behavior of humans, and there is a lot of work to be done. Now, let me talk about something else that is becoming important, is the concept of risk for AI systems. I think that AI is not a threat, it's clear. Like any technology, AI is neutral, and it's our responsibility to use it wisely. It's clear. Now, in fact, when we talk about risks from AI, there are two types of risks, and often in papers there is confusion. There is the technology risk that comes from the fact that a system violates some properties that are in the requirements of the system, and the anthropogenic risks that arise from the intentional or unintentional misuse of technology, and here you can violate legal frameworks. So even if an LLM can generate deep fakes, be considered this as a violation of a safety requirement. However, the law can prohibit the use of LLMs to produce deepfakes. So this is a different problem. Now, regarding the technology risk, because typically, for instance, the AI Act deals with technology risk linked to the use of AI, I would like to emphasize the trustworthiness of all kinds of artifacts is determined by standards. So all the technical civilization relies on the use of rigorous standards. When you buy a toaster and you use it, it's guaranteed that it will not kill you if you use it properly. And unfortunately for ICT systems and later for AI applications, we have no standards with a few exceptions. And today in the United States, the authorities accept also for autonomous cars and medical devices what they call self-certification by manufacturers, which means that, for just to simplify, Mr. Tesla guarantees the safety of his cars, which is a kind, I mean, it's a bit strange because so the responsibility is transferred to the manufacturer. My last slide, and here I would like to say that also the degree of acceptance of AI system will depend also on our ability to integrate these systems in traditional systems engineering design flows. I did not have time to talk about that. I'm working on this problem. Today we have new trends that are disrupting traditional systems engineering. As I said, adopting machine learning based end-to-end solutions to drive cars. There are some self-driving platforms, but these platforms are not trustworthy enough, so they are not used. These are platforms developed by Waymo and NVIDIA. As I said, they allow self-certification in absence of standards. And you know that also they allow regular updates of critical software, so over the air, and this is also something that can be dangerous. So the question is, what are problems in system engineering? I see two classes of problems. One is how to integrate AI systems in system design flows. Okay, so how to marry database systems of which we can guarantee the properties and non-explainable systems. I think that non-explainability should not be a problem because we know since von Neumann how to build trusted systems from untrusted components. I think for AI systems, we should consider how restrictions on training data sets allow better predictability and controllability. And this is something that is, for the moment, big tech companies completely ignore. For instance, when LLM explains how to make a bomb, it sums up information acquired during its training. So one may wonder why the LLM had access to this kind of information. Of course, this has to do with how you prepare the training sets, and this is a complicated problem. And also, we should strive to explore new avenues for explainable AI. Now, regarding also system validation, what is important to remark is this shift from rationalism to empiricism. So all the strong properties of traditional systems are based on the use of models. So when, for instance, you guarantee the trustworthiness of a flight controller, and you say the probability of failure is less than 10 to the minus 9 failures per hour of operation, you do some calculation and you are using models. And here we cannot use models. So we will, so there is a shift from rationalism to empiricism, as I say here, but simulation is not enough, and we need, in my opinion, statistical testing techniques. And this is a big challenge, how to develop statistical-based techniques. And of course, another important question is that we have to live with weaker transconfidence guarantees, because we will be able to apply only testing techniques. And I think that this can be offset by the use of knowledge-based techniques. But okay, I will not explain this idea right now. So if you have questions, I will answer. And so just to conclude, I will say that the transition from automation to autonomy, which is a step toward AI that matches human intelligence, cannot be progressive. We thought that it would be progressive, and we need to develop a new scientific and engineering foundation. This will take some time. So this slide, I will conclude my talk. There is a paper on testing system intelligence that you can find. And also I advertise my book that discusses many of these issues I have presented. Thank you for your attention. Thank you.
So thank you very much for this interesting talk. I would like to ask whoever wants to ask a question to please come here, and we can have a line up here. So please feel free to do that. And people from Zoom can also ask questions. Let me start with the following question, and this is something that you mentioned on your last slide. So this discussion about system validation. So in the past, for critical systems, we had these formal validation processes. I forgot to mention that, but several of the ideas developed by Professor Sifakis are now what makes planes and ships run safely. So this was part of the design of these complex systems in the past. Nowadays, with autonomous vehicles, we have bypassed that. And it seems that machine learning, deep learning is probably a non-escapable future of this kind of systems. So since we are lacking in terms of validation of these systems, where do you think that we're going? You mentioned some ideas in your last slide. Could you please elaborate on those? So do you think that we can build validation systems on the current AI methods, or do you think that we need new AI methods that will encompass somehow validation in them, taking into account that these kind of systems are now already in use, right? So these systems that cannot be validated are moving ahead.
Yes, okay. They are already used. You see, even for a Tesla, there are some restrictions. They recommend that you use the self-driving features only under some conditions, okay? So if the weather is foggy, or I don't know, I mean, I think you are taking risks. And what we find by analyzing real simulators is that there are a lot of problems. Of course, the problems we find we find these problems because we're applying a theory, and the probability of these faults to occur is perhaps very low, especially if you are considering normal conditions. And okay, but if you have millions of cars driven, then the probability will be higher. And also, I think that the big tech companies, the American companies, are pushing a lot in that direction. But I'm not sure that the Europeans will follow that. And Tesla, at least in Europe, is not qualified for full self-driving. And Tesla does not, they don't claim that they have full self-driving features. Now, there is a lot of pressure, there are a lot of arguments, there is a kind of war, okay, and many of these arguments are completely, I mean, technically not sound. I think that in the future, in fact, we should study some architectures. I'm working on that. where we will have, say, some untrusted system that will run in parallel with a trusted system that is certified. Typically, for instance, for self-driving cars, we could have run in parallel another system that is a collision avoidance system that will take over when the non-reliable system is likely to fail to manage a situation. The problem with this solution is the transition from the untrusted system to the trusted system because, okay, they have different dynamics. I mean, there are technical problems we don't know how to solve. And also the idea in these architectures we call runtime assurance architectures is that the trusted system passes back the control to the untrusted system in a smooth manner. So because many of the flows of the untrusted systems of AI systems are transient. So for some reason you have some kind of anomaly, and so these are solutions that are currently being studied by automotive industry. Something else that I would like to emphasize because this is a problem many people in industry ignore and they have recently discovered is that assume that you have now a self-driving platform that uses an end-to-end solution neural network. So you receive, say, frames, and you produce steering angle and braking signals, whatever. Okay. Now, once you have this, you have to integrate this into an electromechanical system. Now, what we know in classical systems engineering, how to integrate a system of whom we know the structure, okay? And there are techniques that are risk analysis techniques. If I have a flat tire, how I propagate the effects of a flat tire. Now, if you have a conventional system, you see how this is propagating in some structure. But if you have a monolithic AI system, this will not go. So this is the reason they spent billions of dollars to develop AI-enabled end-to-end solutions. They don't use them. I mean, NVIDIA and Waymo, or they use them experimentally. And they are facing this kind of problem. But I should also say that there are other companies that try now to, by using LLMs, to find architectures where they decompose the different functions. So this is closer to traditional systems engineering. Okay, there is a long way to go. I'm not saying that it's hopeless, but you should not consider that currently we have the state of the art allows full autonomy for plenty of self-driving cars in big cities. Okay.
Thank you. Pavlos has a question.
I have two, if possible. The first one is the following. If we have systems built on theoretical models for which we have proven properties guaranteeing that the system is going to behave always correctly.
Yes.
Do you need still a testing system for
yes, but you cannot solve the autonomy problem. You cannot solve it exclusively by using model-based techniques because you will be using perception, for instance. So at some point, you should connect, even if the decision-making system is model-based. So you are using classical algorithms for decision, and we have very good algorithms for that. The perception system is data-based. So you have to, so there is a connection, and this is a very hard problem we don't know how to solve. So probably you've noticed, and this is the reason also that Tesla, for instance, they are using only cameras, and they don't, they could have built more reliable solutions. They don't know how to do that. The question is how you link the database information from sensor information. For instance, we could have also some map repository and to connect, but maps are symbolic information, okay? So how to connect database and symbolic information? That's a hard problem. It's, yes.
Okay, in this context, yes.
We have to live with the two worlds, and this is a big challenge. Yes.
Okay? So the second question is, if we talk about multi-agent systems, okay, we have several
Yes.
agents.
Yes.
Is it enough? I have my idea, but I would like to have your opinion.
Yes.
Is it enough to say that the system globally is going to behave correctly if we guarantee that each one of the system is
No. This is something I did not discuss, but I discussed extensively in this paper. So you should distinguish between agent intelligence and collective intelligence.
Right. So
And this is something that is completely ignored. Let me give examples, because we see the problems with self-driving cars today in San Francisco. Okay, you have, just to adopt an agent terminology, agent-centric terminology, you can have selfish agents. Okay, stupid agents. Okay, it's safe, but it stays there. It blocks the traffic. Okay, so and this is something that is not considered at all for the moment. So I have a car that drives safe, but it's not enough, because if it drives safely and it stops in the middle of an intersection, or it blocks a police car. Okay, this is an issue, and this is in fact an issue in San Francisco, where they are doing these experiments. So there is a long way to go from individual intelligence to collective intelligence. And this is not at all discussed. And what is clear is that to achieve collective intelligence, because you have a distributed system, this is a system engineering problem. You need protocols, distributed algorithms. This has nothing to do with the fact that the agents are intelligent or not. They can be stupid or intelligent. You have to coordinate agents. Okay. And these systems engineering problems are completely ignored by the AI guys. Yes. Thank you for the question. Yes.
Yeah, that's why, for example, in negotiation system, we need also, I can imagine, to test the trustworthiness of the negotiation protocols of
course, yes. How to achieve consensus. And what characterizes, by the way, human intelligence is social behavior. Okay, we have a way to achieve. In my book, I discuss this very, very important issue on. So, if you consider the humans are computing systems, okay, then you see that they have also a specific way to decide, to make decisions and coordinate. And these are value-based systems. And value-based systems is the category of systems for achieving consensus that are very, very interesting. Okay. Thank you for the question.
Thank you.
Yes. Okay.
We have a question from the audience here.
Thank you very much for a very interesting talk. So I just had a question on the management of the risk of AI. So as you already mentioned in your talk, so basically recently we have a debate, like a controversy in the management of OpenAI. So basically the debate starts from like whether we should go ahead with something like they call super alignment, or they call like something
like, sorry, I did not get something like.
Yeah, sorry. So basically there are two decisions. So the first option is they call them super alignment. So basically they want to develop the AI to align the function of AI to be with the human values.
Yes.
Second one is like they call it effective accelerationism. So basically the idea is that in order to avoid some risk, we should further faster develop the technique so we can get over it instead of like over focusing on the current state. So basically there is a heated debate over these two ideas between these two regions.
Okay, but these are religious debates that are not technical debates. These are completely, I'm shocked to see papers by famous people who talk about ethical alignment. Okay, because if you try to analyze it means ethical alignment, it means that a machine will behave like a human in making choices. Now, in order to, as an engineer, the way I understand the problem is the following. First, I know how a human makes ethical decisions. And then, of course, I will say, oh, I have a model of how the human, which I don't have today, okay? And then, so in many papers, you have a game between a player and the system, and the judge is, so you don't have objectivity about that, okay? And the guy says, oh, this is fair. I decide that this is fair. So you can discuss whether it's fair or this is responsive. This is too bad for science. And I think that we as researchers and academics and scientists, we should fight against that. There is a lot of pollution because of this kind of stupid papers that are not technical. Now, the problem is that a lot of people are pushing, and if you see also when they make proposals about governance, AI governance, they mention these principles. I have nothing against the principle, but the principles are not enough. If you say my system is safe for different kinds of functions, you should define technically what it means safe. And not only define this, but you should provide according to, I mean, the scientific method requires that you give also the method to test that this is okay. So you should provide the test method. I mean, this is elementary in the philosophy of sciences, okay? And people are forgetting all this, and yes. So I mean, this is crazy. Okay, I don't. So the second avenue, I did not understand what you said, so I prefer not to comment on
Sorry,
this.
the second one is he calls them effective acceleration. So basically, they want to see...
I don't understand what it means. Okay, already, you see the concept of alignment, and these guys also are very good at inventing a new terminology, because alignment is a homomorphism. I mean, with my old background, the technical background, I understand that this is a kind of homomorphism of behaviors, and we have techniques also to check homomorphism of behaviors. Okay, and I mean, it's yes, it's sad that all this, yes, you have this kind of ideas, and that are also mobilizing a lot of people and a lot of discussion. Yes, thank you.
Thank you very much for your comments.
Are there any other questions from Zoom or from the audience? Let me ask one last question. So at some point in your talk, you mentioned about the work that you're currently doing on implementing some tests for existing systems. So what are the ideas there? How can you start formalizing this area?
Yes, okay. First of all, you need to have a formal model of what is the world. So we have defined what is a world, I mean, an abstraction of the world. It's a graph, it's a metric graph. So you have some theory about what is the world, and in fact, we extract from high definition maps this mathematical model of what is the world. And this is, we know how to do that, in fact. So, and then, of course, the problem is that you can have scenarios of infinite length, okay? So the idea is to compose the scenarios. You say that you identify the critical scenarios, and also we have a theory about what is a degree of criticality of scenarios. So you can imagine that one scenario. So first of all, we apply compositionality principles. So for different configurations, we decompose the map into sequences of configuration. So for instance, you are driving in a highway, in a lane, you merge into a road of higher priority, you have different types of intersections, etc. So the assumption is that driving a car is a combination of skills. And these skills, you use them to drive in different configurations. So I know how to drive in a roundabout. I know how to cross an intersection that is guarded by traffic lights and things like that. So we have a collection of situations, and for this situation, and then of course we have some theory that, so for each of these situations, we have the theory. So this limits the complexity, in fact. And then we have a theory about how that, to show that a general scenario is a composition. So if you are safe in this configurations, then you will be safe in any. So this is in a paper that we are writing currently, but this is the idea. Now, what the method that gives a lot of interesting results with industrial simulators is that we analyze the approach, what is a maneuver of a vehicle, and we have a theory about what is possible and what the most self-driving systems don't do. It's very interesting to analyze real-life systems. Yes.
Okay, thank you very much. If there are no other questions, so I would like to thank Professor Sifakis once again.
Thank you. Thank you for inviting me. Okay. Yes. Thank you.
Thank you very much to all for participating. Thank you, Joseph.
Thank you. Okay. Bye. Bye, everybody. Thank you.
Bye-bye.
Bye. Bye.